Okay, good afternoon, everyone. Welcome to the KNI Distinguished Seminar. The speaker today is Professor Hong Tang from Yale University, and he's a professor of electrical engineering, physics, and applied physics. Hong has deep roots here at Caltech. He was actually a PhD student with Michael Rukesh, and then he also was a postdoc and scientist. Also Professor Rukesh, and he is responsible for setting up a lot of the tools that actually you are using in KNI, including the first e-beam writer. That's correct? Yeah, right? Yes. And Hong and I first met when I was an undergrad here at Caltech doing a project with Michael Rukesh, and he was a postdoc in the Rukesh lab. So he moved to Yale since 2006, and since then he had a very successful career. He got the Packard Fellowship, also the NSF Career Award. These are young faculty awards. He's no longer that. He's very well established now. In Michael Rukesh group, he did a lot of work on mechanics. Since going to Yale, he really diversified and added optics into the mix, and now he's doing a lot of work integrating optomechanics and electro-optics, and today he will talk about his recent work on integrated Ki-2 photonics.
Well, thanks, Andrew. It's a real pleasure to be back at the Caltech and give this KNI lecture. I had a really long flight yesterday, and I was on an airplane and looking for some older photos. There are a lot of fond memories. Some of you in the audience, I don't know if you remember, this one of these first e-beam writers that was set up in Michael Rukesh's lab down in the Sloan Laboratory. And that was me 70 years ago doing e-beam lithography. And this was me that have a lot of fun to play with this helium-3 tiny refrigerator. I think it's still being used today.
No, I used that ACM too.
You did, yes. So with all this hard work, I was given a piece of paper. What is this? Why there's arrow moving around? I got a degree in condensed matter physics, and after that, I stay around and work on an unsuccessful company. And in part-time, I work as a guy, set up some of the tools, including the e-beam writer and some of the etcher. And this later become the KNI facility. So that was a lot of fun. At Caltech, I was working on magnetic semiconductors. Out of a Rukesh's lab, I never touched any optics. I don't even know what some laser looks like. Never touched any fiber, never touched any mirror. So after I went to Yale, we decided to work on photonics. So here's me again. I was very happy and very lucky to be able to recruit a graduate student from Rukesh's lab, Moni. And he and I, with the help with some Sharers group alumni, we built this photonic chip with a mechanical resonator that embedded this silicon photonic chip. And Mo was able to write a series of papers, study the light interaction with the mechanical structure, look at the force applied by light. So this work earned Mo a faculty position, also earned my tenure at Yale, which was quite hard. So this is the start of my journey in optics. And today I have a group of more than 15 people working on different optics, integrated optics platform. And it's a fun working on with optics, as all of you probably realize that. So I'm going to tell you today about integrated Ki-2 photonics. And first I'll tell you why do we need these Ki-2 photonics and how is that different from silicon photonics. And specifically, I'm going to tell you about aluminum nitride. There are many different types of Ki-2 material you can build photonic structures. Lithium niobate is a really very competing material platform. There are gallium arsenide, gallium phosphide, and those are good material. But we think aluminum nitride really have the strengths, and we can build a very nonlinear and some of the quantum photonic circuits. And then I'll elaborate on an important application of this nonlinear aluminum nitride devices is for quantum frequency conversion. And just make a correction, I see that on the website, integrated Ki-2 is not qubits. Actually, it should be quadratic. It need to be corrected. Okay, so in terms of integrated photonics, silicon photonics by far is the most established platform. And today, you can use a CMOS foundry to build a very complex electro-optical circuits to perform a lot of functions, mostly in communication domain. There's a successful story of like startup company, established company working on this regime. You can also leverage the silicon photonics to build a quantum photonic chips by leveraging the Chi-3 effect in the silicon to create photon pairs and manipulate the photon pairs. So, but there's some shortcoming. Silicon is a narrowband semiconductor, and you can only operate the light at wavelengths longer than 1 micron. So it's actually a big limitation for people who work on quantum optics and also work on atomic physics. In those cases, you always work with the very visible photons. So other drawback is that silicon crystal has a symmetric structure, and that means that silicon does not have Ki-2 nonlinearity. And the Ki-2 nonlinearity is some of the most important element in quantum photonics and atomic physics. With the Ki-2 nonlinearity, you can build an electro-optical modulator and second harmonic generator, frequency conversion. Silicon cannot offer that. So aluminum nitride, on the other hand, can make up all those drawbacks in our mind. And so aluminum nitride is a very well-known MEMS material. And today you have those F-bar filters that are built in your cell phones. So those process quite a big scale wafers. In particular, the most recent advance in solid-state lighting make a nitride, 3 nitride, very industrialized material. So as a matter of fact, the 3 nitride is the second most manufactured semiconductor only after silicon. So there are a lot of industry infrastructure to create those materials. And aluminum nitride has a very large band gap, more than 6 eV. That means it is transparent over from mid-IR all the way to UV. So this is very important. So that means that you can operate this device at a very high power with very good linear and nonlinear properties, because it does not have interband absorption with most of the wavelengths that we are concerned with. So there are 2 different methods we fabricate aluminum nitride thin films in the lab. The first approach is just like a MEMS approach. You sputter aluminum nitride on your substrate. Normally in the MEMS, you sputter on metals. So back about 10 years ago, a student decided to sputter direct on oxide. Oxide is an amorphous substrate, and magically after sputtering, the domain of aluminum nitride actually all line up. C-axis all line up. So this is just thermodynamic at play. So they align, all those domains align within 2 degrees. So you can measure that through X-ray rocking curve. And the surface is also pretty smooth. So the roughness is about 3 nanometer. So each of the domains is about 20 nanometer. That means give you very little scattering of light. So those are polycrystalline material, and they're also single crystalline material. These are really advance of the solid-state lighting industry give you this film that can be grown directly on sapphire. So most of your LEDs, the sapphire is cheap, right? So they grow on sapphire. Gallium nitride grow on sapphire, produce very efficiency as LED. So you can make large wafers, like 2 to 3 inch wafer, make many of them. And those are lattice matched. You can look at the TEM image, you can see the atoms in X-ray rocking curve, give very narrow line width. And the surface roughness also go down by factor of 10. It's a very smooth structure. So with those structures, you can get a very high Q for both of those film in the mid IR, and visible band. You have a Q more than million. With a single crystal material, you can get a Q almost a quarter million in the UV band. So very no loss material. So how about nonlinearity? That's a linear property. So the nonlinearity of the aluminum nitride arises from the kind of wurtzite crystal structure, have a bulk inversion asymmetry, and that gives you this lowest order optical nonlinearity, which is Chi2 nonlinearity or quadratic nonlinearity. And these are the nonlinearity we like to utilize for frequency conversion in our devices. Any material would have a Chi3 or cubic nonlinearity. So silicon have a cubic nonlinearity, which is the lowest order nonlinearity. And aluminum nitride also have a cubic nonlinearity that give you kind of a foil mixing process. So in aluminum nitride, we have studied quite many different kind of a nonlinear effect. Really the combination of a Chi2 and a Chi3 effect. So through the Chi2 effect, you have an electro-optical modulator. That's a Parcells effect. And you have a second harmonic generation. You have a different sum frequency generation, parametric Tang conversion. You can build an optical parametric oscillator. With Chi3, you can have a third harmonic generation, frequency comb, Sonneton generation, Raman comb. You can even combine this Chi3, Chi2 effect, have a new phenomena. And you can push always to the UV, make a UV comb. So among all those nonlinear effect, in our mind, this second harmonic generation is the most important. It's best indicator of nonlinearity of your devices. So let me just start talk about the second harmonic generation. Okay, so for second harmonic generation, one very important thing to do is to have a phase matching. So if you work in lithium niobate, you know that the fundamental light and the second harmonic light, because of material dispersion, they have a different phase velocity. So you match that by periodical polling, so create that lattice vector to compensate your momentum loss in this conversion process. But aluminum nitride is a piezoelectric material. It's not a ferroelectric material. You cannot pull it. So we have to find a different way to do this phase matching, what we call the modal phase matching. The idea is that you vary the width of this waveguide, okay? Then when you vary the width, the effective refractive index of the fundamental mode of light change as you change the width. And you look at one of the higher order mode of the second harmonic mode. For example, TM2 mode here. They have a different curve. At one point, they're going to cross each other. For example, at the waveguide width of 1.1 over here, this width, then you have your phase matching point. So you have two modes supported by this ring resonator. One is the fundamental mode here, one is a higher order mode of at 2 omega frequency. Now, you need to design a launching waveguide to excite the fundamental mode here. This is the coupler down here. That's a phase match to this waveguide. You also design a second waveguide here, which is much narrower, to phase match to the second harmonic mode. In this way, you can excite this resonator with a fundamental light and extract a second harmonic light. This phase matching has a very critical requirement on the device dimensions. So as a matter of fact, if you change the width of the waveguide by 1 nanometer, your phase matching window shift by 1 nanometer in wavelengths. So this is very hard to control, and my knowledge in beam lithography come into play. And so what do we do? Normally, we make an array of these resonators here. So here's a pair of waveguide. You multiplex a number of resonators on the same set of waveguide. Each of these ring, the size change by 10 nanometer. So this is an example of a transmission through an array of 8 resonators. You see the 8 resonance, okay? And they're separated by about half a nanometer. So you can make more, you can fill the space over here. That allows you to really dial in the wavelengths you want. In particular, when you want to access like atomic transition, that's pretty much the only way to do that. So how do you have your phase matching? It's quite easy. So you put your device under microscope, you send the IR light in, and you look at the microscope, with the microscope, you can see the light up. You see the visible light coming out, so you know you're phase matched. And so the past years, we've been improving our second harmonic generation efficiency from early days of 0.4% per watt. Right now, it's about 17,000% per watt. So we have a curve here for 80 years of improvement of second harmonic generation efficiency here, okay? So you can see why you're so obsessed with this number, 17,000% per watt. For very important reasons. We like this number as high as possible because that's an indication of how nonlinear your device is and how efficient you're doing making color conversion of light. Same thing over here. This change to green light from a red light to green light, right? So if you look at this second harmonic generation curve, the horizontal axis over here is the fundamental mode power, and this vertical axis is the second harmonic mode power. And this is a quadratic nonlinearity. That means it's a slope over here. If you plot log plot, the slope should be 2. But when you increase the pump power, it deviates from this quadratic dependence. So it becomes almost linear over here. So what happens that your conversion efficiency is so high, you deplete your pump, okay? Your pump converts to second harmonics, and they convert back. So your efficiency is not a quadratic dependent anymore. So this deviation from this quadratic dependence tells you the threshold. If you operate this device in an inverse way, instead of doing second harmonic generation, do parametric Tang conversion, and that's the corresponding threshold of your OPO. Okay? So if you have an OPO, you can make squeeze light source, and you can make photon pairs. And if you have this high efficiency, you can make a very efficient quantum frequency converter. And that's the reason we push for this number. I should mention that in lithium niobate, our recent device is 10 times better than this. But from stability point of view, aluminum nitride is still better in device performance. Okay, so let's talk about OPO. So now we're not making second harmonic generator, we're making Tang conversion. So we're not pumping at 1550, we're pumping 775. So this is a device made of single crystal aluminum nitride on sapphire. And so these devices have a 17,000% per watt second harmonic generation efficiency. And that convert to these, if you look at this Hamiltonian, so this regular oscillator mode, you have here a squeezing Hamiltonian over here. So one photon split into 2 photons. And it's a G0, but it's a single photon nonlinearity. That's 17,000% per watt correspond to 80 kilohertz single photon splitting rate. Okay. So if you have certain photon number in the pump mode, this number gets enhanced. If your gain from your pump exceed your loss, then you have an oscillator. And that's exactly what happened in this device. So you can see that at a degenerate case, you get a phase matching and you get a degenerate OPO. Now, if you tune your temperature away from your phase matching point, you get a non-degenerate OPO here. These are lasing, so it's a Chi2 lasing mode. You have a parametric oscillator above threshold. And these OPO operate over the whole C band plus L band. Pretty tunable laser over here. So what's interesting about the line width of this OPO, if you look at the degenerate line width, it just match your pump line width. So it's copy the pump line width. But if you look at a non-degenerate OPO, the line width is almost double. So you have a non-degenerate case, you have a flying wheel in your phase as not as defined as degenerate OPO. Certainly, so these OPO would be a nice thing to have a source on the chip, fully tunable. If you want to work in the quantum domain, you reduce your pump power, just go below the threshold, you have a squeeze light, right? If you go further, reduce the pump power, you generate photon pairs. Those are called spontaneous photon pairs. And so this is something we have demonstrated before. And so you have this same device with a lower performance, but if you want to generate a pair, you don't really need that high efficiency. So you pump out 775, produce a pair of photon with a nitride chip, send out. So we fabricate another device with a 2 single photon detector out of niobium nitride nanowires with a beam splitter after it. So the photon pairs come over here and split over here. So if your photon are bunched, produced in pairs, you should see the photon bunching at these 2 detectors. Those detectors work at 1.7 Kelvin, and you can see that. So you can see the bunching of photon pairs at the degenerate case. You can also operate the non-degenerate case. You capture the signal photon, and you detect there's an idler photon over here, send it to the beam splitter. You see, so you have a heralded single photon source. You see the anti-bunching in the detected signal. So pretty pure photon pair source. It is pure because we don't have a mode problem. All the mode transverse single mode over there. So this photon pair is very well defined. The rate of these photon pairs is about 3 megahertz per milliwatts. So pretty high photon pair generation rate. Of course, you can work in the intermediate regime to generate squeeze light. In that case, it's much harder to measure. You need the detector, photon number resolved detector on the chip, which we don't have right now. So that's kind of application in quantum photonics. So I mentioned earlier that nitride also has this chi-3 nonlinearity or cubic nonlinearity. And you can also generate OPO with the chi-3 effect. In this case, you go back to pump at 1550 nanometer. And you do dispersion engineering. So this is chi-3 dispersion engineering to make sure that you operate the device in this anomalous dispersion regime. If you do that, you can get a frequency comb out. And this is something we just recently got, unpublished result. And we have octave spanning comb. This is a sonneton comb from aluminum nitride. So these are actually the second material platform that produce the octave spanning sonneton comb. The first being the silicon nitride. So the benefit of using aluminum nitride is that aluminum nitride is a chi-2 material, right? So if you have an octave, for example, I can pick one comb line over here, and I double it, overlap with this dispersive wave over here. I can have a self-referencing on the same chip. So we have a fully self-locked sonneton. And this is very important for atomic clock and for frequency metrology. So that's an ongoing progress. Feel very promising. But what's more interesting is that you could actually engineer this device to have this cascade chi-3 and chi-2 effect. Imagine they have an octave spanning comb over here through the chi-3 process like this, okay? So that's generated by chi-3 phase matching. If you are able to simultaneously realize chi-2 phase matching, you could double that sonneton comb and could make an even multi-octave comb. So if you double that, you can really expand your comb to even shorter wavelength regime, fully to the UV band. So as you can imagine, this phase matching dispersion engineering of this device is really challenging. And you need a chi-3 phase matching and chi-2 phase matching in the same device. We have not got there yet, but we have some success. With a narrowband comb, you can do that. So we engineer a device, have an enormous dispersion, very robust, with different weights of the resonator. You can generate almost identical comb at 1550 nanometer. Now, you bring in Chi2 phase matching. You tune your phase matching window across this comb span here. As you can see that in the middle, where the Chi2 phase matching and the Chi3 phase matching exactly overlap, you have a maximum power conversion from this fundamental comb to the second harmonic comb. If you detune from that, your power conversion efficiency drop, but your comb span get wider. So it's just a proof of principle that this can be done. As you can imagine that in the micro resonator, it's much harder because you have to get all the light in and get all the light out, right? It will be much easier to do it in the straight waveguide. And so if you just have a straight waveguide, you dispersion engineer the waveguide cross-section. And this device is so non-linear, if you use a femtosecond laser to pump this waveguide, you can depend on the geometry of this waveguide. You can have a red comb, yellow comb, and a purple comb come out of the device. Your eye really gets blunted by this strong non-linear of this 10 millimeter long waveguide. It's a really strong confinement, very good dispersion engineering. So what's more interesting, how do you get a UV band? It's still visible, right? The way to go to UV band is now you bring a section of this waveguide to satisfy your Chi2 phase matching. And you take this red comb over here, and you double it, okay? So the way we double, we make a multi-section waveguide. So we adiabatic taper the width. So make sure each section of a spectrum can have an opportunity to be doubled. So we can produce like 100 terahertz UV comb over here from 350 to 450 nanometer. So this visible type of comb is very important for exoplanet studies. So that what you want is somewhere over the visible band, have an evenly spaced comb to calibrate their spectrometers. Okay, so that is the nonlinear part of the aluminum nitride device. So before I move on, I just want to ask you if you have any question regarding the previous part of my talk. Yes?
What has been the main driving force for this improved conversion efficiency curve that you showed over the past decade? Is it quality factors or?
Yes, so what is the main driving force for the improvement? Like it's a 5 order of magnitude improvement, 6 order if you consider lithium niobate, right? The better phase matching, higher Q, and all these contributed to the improved efficiency. So we just zoom into the windows that they have good phase matching and keep driving that. Yes?
Do you know off the top of your head what's the effective nonlinearity for your model phase matching?
That's actually a very good question. I worked on this material for 8 years. I still don't know the exact Chi2 numbers, and I can give you a range. It's from 1 to 4 picometer per volt.
If that's effective after model phase matching?
No, that's the material property. After full model was just on the order of 1 picometer per volt. Something like that. There's another question, yes?
What is the rep rate and pump power of the octave strand microcomb?
So what is the repetition rate and the pump power of the octave spanning comb? The repetition rate is about 300 to 350 gigahertz, 300 to 400 gigahertz. The power is on the order of 500 milliwatts in the waveguide. So there's a range of a power. Yeah, so this actually, we don't rely on terahertz comb to get octave. Any other questions? All right, let me move on, talk about the quantum frequency conversion. So that's really an application of these aluminum nitride nonlinear devices. So, so why do we need a frequency converter? As we know that many different species of qubits are now being studied in the quantum science and the technology areas. You have trapped ions, and you have transmon qubits. You have trapped atoms, color centers, spin qubits, and photonic qubits. So each of these qubits have their advantage and disadvantage. So for future network, as one of the papers that point out by Professor Kimball, that you like to make a network of those qubits. So unfortunately, all these different qubits have a different excitation frequency or wavelengths. So if we want to build this network, we need to bridge the gap of their frequencies. So you need this converter to work. So in essence, you need two types of converter to network all those different qubits. You need the optical-to-optical converters. Okay. You also need a microwave-to-optical converters. Okay, because we also have superconducting qubits, which will operate in the microwave frequency regime. So at Yale, we have quite a number of dilution refrigerator. We wish one day we can network all the 13 dilution refrigerator together with a microwave-to-optical converter. So I'm going to tell you how we're going to realize this two type of converter with aluminum nitride devices. Okay, so what do you mean this quantum frequency conversion? So you can think of your quantum information as basically encoded on the carrier. So your converter should be able to copy this sideband from one carrier to another carrier without changing the statistic of the photons. And you can also think of it as an IQ space, and after demodulation, your IQ space representation should be the same, or Wigler function should remain the same. So your converter have one very basic requirement, that's it should be unitary. You want no gain, low loss. You don't want a thermal noise coming into your converter. And you also need some bandwidth to have finite information to pass over. So that's the requirement of your converter. And that's the goal of our devices. So, so how you do that with this Chi2 device? So I mentioned earlier the device operates in a kind of a degenerate mode. So for the converter, we often operate in a non-degenerate mode. So you have a signal idler and 2 omega mode. And so here you're really mixing Hamiltonian, and A and C is the fundamental mode, and the B is the second harmonic mode. And now, if you drive one of the mode over here, for example, A mode, the signal with a coherent tone, replace the operator with a number, and you get a beam splinter Hamiltonian. So if your system is lossless, you get conversion of excitation from C mode to B mode and backward. Of course, so this G is a very important parameter, which is directly proportional to the mode lap of the 3 mode in the Chi2 nonlinearity. So larger Chi2 nonlinearity, the larger the single photon coupling rate. And this A square root of a photon number in your pump mode, that's also enhance your conversion efficiency. And also loss. And we have to consider loss. The way to consider loss, you introduce this cooperativity, which is the coupling rate squared divided by the external, the line weights of each of these coupled mode. So this eventually, this C cooperativity proportion of the quantity factor over the mode volume. So higher quantity factor, reduce the mode volume, all important requirement to make efficient converter. So I should mention that this ABC mode is not limited to photons, and it could be microwave photons, could be photons, could be magnons. As long as they're coupled, as long as you have stereo mixing, you can make this converter to work. And that's why you can use the same Chi2 nonlinearity to make microwave-to-optical converters. And we also work on Magnon and photon-based platform. So to make an optic-to-optic converter is relatively straightforward. It's a concept that has been established in the community. And for example, this is a second harmonic generator. You operate in a non-degenerated mode. So you put the one with the pump mode over here, which is your red tone over here. And then your fundamental mode coupled to the harmonic mode through this pump drive. So you can think of this resonator as two resonators coupled together by a G. This is G enhanced by your drive. And so what happened that you can measure this cooperativity directly by looking at transmission through this visible, what I call visible 778 nanometer light. So as you increase your drive from 0 dBm to 0 milliwatts to 80 milliwatts, you can see that at the beginning, your resonator is linear, just a Lorentzian deep transmission. But as you increase the drive, you can see that it's a transparency one day start to build up. So what happened that this coupling becomes stronger, you have a coupled mode, your mode starts to spin it, because you have two modes over there. So how much of this transparency tell you what your cooperativity, just through this transmission measurement. So that's just a linear probe of this resonator at a harmonic frequency. So if you operate the device in the conversion mode, what you do, you send visible light in, and with that drive, measure technical light. Or backward, you send the technical light in, with that drive, up convert to 7780 nanometer. You can plot this conversion efficiency curve as a function of pump power. And this pump power convert to the cooperativity. You can see that they convert optical to optical conversion, forward conversion, backward conversion, they fall on the same curve. This curve peak at a cooperativity equals 1, which is predicted from this coupled mode theory that this, look at this factor over here, this factor maximized at a cooperativity equals 1. So when your cooperativity is small, your conversion efficiency is weak, your pump power is small, of course your conversion efficiency is going to be small. When your cooperativity is too high, you overdrive your device and convert it back, so your efficiency goes down as well. And so in this device, we have a 14% of total conversion efficiency, even though this internal conversion efficiency is 100%. The reason that when we first designed this device, we wanted the signal in the harmonic mode to be critical coupled. This turned out to be not the best design, because if you look at this conversion efficiency, this is a pre-factor, corresponding loading factor. So if you are critical coupled, this is a 50% here, and this mode also 50%, you would expect only 25% of total conversion efficiency. So if you want to drive this device to have 100% conversion efficiency, you would like to have this both mode to be overcoupled. So this is very important to realize, to have optical mode to be overcoupled to have high efficiency, so you are not lost by this coupling. So again, the reason we designed this harmonic mode at 778 nanometer or 780 nanometer, really we targeted to address rubidium transitions. And there are two recent papers we published. In this paper, we tuned the second harmonic mode to match rubidium 85 two-photon transition. That's for the atomic clock application. In another paper, we tuned to the rubidium 87 D2 transition, and also for clock applications. So that means you can use this converter to interface with your code atoms. Okay, then move on to microwave-to-optics conversion. This is a much challenging task. Yes, please.
Did you look at the noise, spontaneous noise? Like with this optical converter operate at single photon?
We did not measure that. We should have, but we thought there was no noise. That's just assumption. We should have measured that. Yeah, we did not measure it. It's optic-to-optical. We never worry about that noise. Yeah, that noise issue become a problem in the microwave domain. So you want to convert microwave photon to optical photon. Remember, your optics 200 hertz, right? Your microwave 10 gigahertz. So there are 4 order magnitude in difference in energy. There are also 4 order magnitude difference in wavelengths. So it's quite a hard task. So there are a lot of work in the community. I'm not listing all over here, but I just want to highlight the 2 approaches through mechanical resonator. My group will also work on mechanical resonator, but this kind of a really nice device that make big progresses. So one work is done by Yale group that uses these membranes that are vibrating at 1 megahertz. And the membrane coupled to a superconducting resonator on one side and also coupled to optical resonator. So this is a 4-way mixing process. And what you have a 2 pump over here. One is a detuned optical pump, one detuned microwave pump. Uses this mechanical enhanced Raman effect. You can convert the sideband from a microwave domain to optical domain. So this is really nice. This device can achieve close to 50% conversion efficiency. And the hard part, this is a mechanical resonator at 1 megahertz. So even you cool down to millikelvin, it's already have a thermal excitation on the order of 1,000. So you need to pre-cool this resonator to make sure you don't have added noise to this converter. And right now, this group can really drive that noise down 8 photons. Very impressive progress. Of course, so this approach pioneered by Oscar Painter's group move this resonator frequency to gigahertz, and that will mitigate this thermal noise problem. And a lot of progress has been made in those along these directions. So you may ask, can you do this Chi2 process without any moving part to make this converter? And so the idea actually was in the community for quite a long time. We had that idea too at the same time. That there was a theory back in 2011, so that you just take this electro-optic modulator, for example, lithium niobate, and you fold back this waveguide inside this modulator into a resonator, and you fold back the driving electrode into a microwave resonator. So you have a dual resonance or triple resonance configuration like this, and you would enhance your coupling between your microwave mode and optic mode and have efficient conversion. So that's a pretty idea, very good idea, but it's very difficult to realize. And it's difficult because of the phase matching I just mentioned earlier. In optic domain, it's already quite challenging. In the microwave domain, it becomes even harder. And here's, after many years of hard working, we figured out a solution to achieve this phase matching. So what you see over here, buried over here is aluminum nitride microring resonator with radius of 100 micron. And there's an layer of silicon dioxide glass. On top of that, we deposit a superconducting microwave resonator. Take a very weird shape. We call it infinity resonator, look like a simple infinity, right? And so this device actually allow us to achieve this phase matching between microwave and optical mode. So when we talk about phase matching, we actually talk about different degree of freedom of mode matching. There's polarization mode matching, energy matching, and angular momentum matching. So, so what are those mode matching problem we have to address? So remember, your Chi2 is a tensor element, right? It's a sort of rank tensor. So you contract and make it look like this reduce the tensor over here, considering the crystal symmetry on the nitride, and those are non-zero element. So normally people use this R33 element to have a high conversion efficiency. But this turned out to be difficult. If you do that, your microwave in the optical modes, your two optical modes, one is a pump, all need to be TM polarized. So when you are TM polarized, your two optical mode, if you are phase matched, they actually have a mode anti-crossing that they will never approach to each other, give your energy matching to the microwave mode. So that's the reason we take 1-3 component of this tensor, electro-optical tensor. And this have a benefit that you can fabricate a microwave resonator with an in-plane field, TE mode or microwave mode. So that the unreduced index 113, so this is a TE mode. The other two modes would have to be TE and the TM mode. This actually is an advantage to do this. So now what do we need to do to have a phase matching is just have this two mode, TE and TM mode, to engineer them to have the same phase velocity like we did before. And so that's the requirement is because a microwave mode have a very little energy. So this is 200 terahertz, right? That 10 gigahertz doesn't really make a difference. That means this two frequencies should be very close. And also a microwave field does not give you much momentum. That means this momentum of these two modes should be very close. So that means your refractive index should be identical for the TE and the TM mode. Within the last digit, 0.001 there, your two modes should have the same index. However, you do not really want the TE, TM mode to have the same mode index. If that's the case, your TE, TM mode actually also have mode crossing because our waveguide never gonna be pure rectangular. It's a TE-like or TM-like, right? So you have this kind of a trapezoidal shape of a waveguide. When your two modes have the same energy, same momentum, they're gonna have coupling, and that coupling can be very strong on the order of 100 gigahertz, and you would not be able to satisfy energy matching. And we actually allow our device to reduce this coupling to have this azimuthal mode number to be differ by 1. So in this case, if they differ by 1, your coupling become weaker, and that anti-crossing could match the microwave energy. So how do you engineer a device to make sure that your two mode, TE, TM mode, the mode index only differ by 1? Remember, your mode index probably are 1600 something. And the way to do it is spectroscopy. You leverage this Vernier effect. So first, your engineering mode have the same to TE, TM to have the same phase index, and you subtract the frequency of each of these TE mode family and the TM mode family. You'll find that the frequency, the difference, will follow a triangle wave. So when the TM mode, just exactly in the middle of TE mode, they have a peak over here. When the TM mode 9 up TM mode, they get 0 over here. If you have anti-crossing, this will never reach 0. Okay? So the larger anti-crossing, this offset is bigger from 0. So you do the transmission measurement of your resonator. So if your TE mode or TM mode are very mismatched, you only see TE mode come through. And also only TM mode comes through. But if they are coupled, if you engineer the index too much, you will see their coupling. You zoom into here, and you see you send the TE mode in, you see splitting of those modes in certain regime. You do this Vernier effect, subtract the frequency difference. You'll see that here you have a maximum anti-crossing. You know that your two azimuthal number of these two modes are going to be matched. We don't know exact number. We think it's a 1600 something. So that the delta M equals 0. Here you have delta M equals 1. And here's the mode you're going to work with in this regime. So that gives you weaker anti-crossing, you work over here. And Then you also need to engineer your microwave to provide that loss of angular momentum. So way to do that, you take this lambda resonator. You make a center of your lambda resonator be fatter and the edge also bigger. Then you fold it over. Okay, doesn't work. So you fold this over. Okay. So fold over like that. Makes that infinity shape. And now you'll see that you actually have two microwave mode. One of the mode, like the field in a radial direction, are the same phase. The other mode, actually, when you rotate it by pi, you see the sign of your phase change. And that means this mode have angular momentum equals 1. And this is the mode we utilize. So this is very important to realize. After we done this, the remaining just a measurement is actually turned out quite easy. So now you have this converter device with two ports. One is RF port, the other is an optical port. You send your carrier in over here and look at the sideband of your carrier. So you can send an RF signal in, okay. You demodulate the optical carrier. You see these conversion from microwave to optics here. Or you can do the backward, send the optical sideband in and measure RF power. You have SEO, so optical to electrical. So you can see that the shape almost identical, but the amplitude is different because the photon energy for microwave is much smaller. So you have much more microwave photon over here input. And with that, you can actually calibrate. There's a procedure established by the GILA group to calibrate your absolute conversion efficiency. It's more interesting actually to look at the reflection from its ports. So if you look at the RF port, you look at reflection, it's very simple, right? Just a resonance. What's more interesting, look at the optical port. Look at reflections. Here you just the optical mode, which have line width about 200 megahertz. And at the bottom of the optical reflection, that mode, you see this superconducting resonance. And that's due to your infinity resonator resonance. So you actually optically drive that resonance and optically read out that resonance. This is electromagnetic induced transparency. The only thing is that we don't have a full transparency, right? But look at this transparency. You can calibrate your coercitivity, which is about 0.075. And that number translates to this factor is about 26%. That means that the internal conversion efficiency is about 26%. The waveguide to waveguide conversion efficiency, so cable to waveguide conversion efficiency, need to be modified by this loading factor. Again, our optical resonator is undercoupled, and also microwave resonator is undercoupled. The total conversion efficiency from waveguide to waveguide is 2%. So these to us is very exciting because the bandwidth is very nice, about 0.6 megahertz, limited by the microwave resonator bandwidth. And we are in the process to improve this device to have a higher efficiency. And so one thing I should point out, the single photon coupling rate for this device is about 300 hertz. This is almost like 3 order magnitude smaller than Oscar optomechanical crystal device. That also means that these devices need to pump a lot harder than optomechanical crystal. We have a bigger mode volume, and that will gain some of the photon numbers. And on the other side, we actually never planned to operate this device at the millikelvin temperature. And if you look at the experiment setup, we operate this device at 1 Kelvin. So at 1 Kelvin, we have a lot of cooling power. And that actually allows us to operate this device. The optical illumination will not impact our millikelvin qubit system. So the question is, if you have a 10 gigahertz resonator, even at 1 millikelvin, your thermal occupation is still like 1.5. You're not at the ground state, right? As I mentioned earlier, you still need the device to operate at the ground state to not add noise, thermal noise. So we can address that. If you look carefully, we have a superconducting cable connected to the resonator itself. So this cable not only provides a conduit for the quantum information to come out of the qubits, but also provide a cooling channel to cool this microwave resonator. The reason is that if you look at my microwave resonator, it coupled to the environment with the intrinsic coupling rate. It also coupled to this antenna with the external coupling rate. So your mode temperature actually much cooler than your environmental temperature. So this is like a radiative cooling, right? Just like our Earth cooled by the universe. So it works. So here we measure the thermal radiation come out of the device. We can see that if the environmental temperature is 1 Kelvin, with this presence of a coupling, we can cool down the device from a 1.5 photon number, thermal photon number, to 0.5 super photon number. Right now, this coupling rate at this point is 66%. If we have further increases the coupling rate to 99%, we can fully suppress the thermal noise in these resonators. And if you are interested in the detail how we calibrate this measurement, and those are really enabled by this parametric amplifier built by Michel Devery. It's a very small noise photon in the measurement. And there's an archive paper on that. If you're more interested, this is our experimental setup. This is our cryostat coming to my lab about 1.5 years ago. And this is a picture taken in the summer after my daughter took a bath, and she's interested in what's going on over here. We have qubits. We have a parametric amplifier all loaded up. And here's a device that's set at 1 Kelvin with at-cube stages. I also should mention that our conversion efficiency with that device is 2%. These will not allow us to do state transfer, because for that you need at least 50% of conversion efficiency. But you could also do a different way. You can run this device in the parametric dark conversion mode, and you can distribute entanglement in that way. And there was a theory paper in collaboration with Liang Jiang and Michel Devery on this scheme. Even with an inefficient converter, we can distribute entanglement between remote cryostat. So with that, I'd like to summarize my presentation here. I tell you about the Ki-2 photonics, really about the 3D mixing, right? Not only in optical domain, but also in microwave domains. I should really emphasize there's other material, very promising material, like lithium niobate, gallium arsenide, gallium phosphide, 3,5 material. They all can be used to build those converters, the effort on that. We also have a more recent result with the lithium niobate. You can see that it's a periodical pooled ring resonator. And these devices have even better performance than the aluminum nitride. At this point, we have a challenge to stabilize this device because the material has a photorefractive effect at room temperature and also at no temperature. Here, I'd like to acknowledge my group members and my collaborators and the funding agency. And thank you very much for your attention.
Take some question. So for aluminum nitride, so when you deposit on silicon dioxide, the domains align.
Mm-hmm.
Do you know what?
C-axis aligned.
Do you know what makes aluminum nitride special that these things happen?
I don't know. So thermodynamics doesn't work.
But is it common, or it's just a peculiar?
I think
case?
it's a common. So, for example, if you want to make a lithium niobate crystal, it's quite easy to make, right? So, if you want to make a salt, put in water and cool it down and make crystals. So, it happens.
Well, in solution, I know, but when you deposit it, I find it more curious.
It happened. We used to work on this yttrium iron garnet. So you make a kind of a precursor liquid, heat it up, put on a near glass. It's crystallized on glass, and the material just is magically they make the bond with each other.
Mm-hmm. Okay.
Following up on Andre's question, have you thought about other ways of depositing aluminum nitride? Does ALD work? Or do you just stick to sputtering because sputtering worked?
I think you can do ALD. The rate is very slow. So if you operate the ALD for like 3 days, you probably get a 200 nanometer film.
Is the film quality any better? That it's worth it or not?
We tried, and I don't remember. We tried to use it as a dielectric. I think it's not very promising. No, it's not very promising. Single crystal aluminum nitride is good.
Any other questions? Well, if not, let's thank the speaker.
Thank you.